Okay, we are starting chapter 4, which is dealing with antiderivatives and indefinite integration in section 1. So an antiderivative, a capital function f is an antiderivative of little f on an interval I if capital F prime is equal to f. So pretty much what we're doing is going backwards from derivatives. So what this whole definition is saying is if capital F is an antiderivative of little f on an interval I, then g is an antiderivative. You're always going to add on a constant c, because if what we're trying to do is figure out, like in this first example, we're trying to figure out what function has the derivative of 2. That's probably what we're trying to figure out. So thinking back to all that we've done with derivatives so far, we're thinking, okay, so what do we have to take the derivative of to get 2 as an answer? So our answer for y is 2x. And what the whole definition up above is saying with the constant of integration is that whenever we take an antiderivative, we need to add on some value c, because we could have always, if we took the derivative of a constant, it goes away and it's 0. So there could have been a constant on this original function y that we didn't know about. Given this definition down below, y equals it's called the integral of f of x dx equal to capital F of x plus c. So what this question is asking is, what is the integral of 2 dx? And our answer was 2x plus c. This next page is just a bunch of derivative rules and integration rules in the same page, so you can kind of see forward and backwards what all these rules are. So we might need to reference this a couple times, especially for these trig functions. We know them as derivatives, but we're not really confident using the integral side yet, so we need to look at those 6. Okay, describe the antiderivatives of 3x. So one of the rules on the previous page was the pretty much backwards of the power rule. Remember, when we take the derivative, we bring the power down, and so multiply by that power and then lower the power. What we're doing now to find the antiderivative, or integral, of 3x is we have to raise the power and divide by that same number. So the 3 stays on the outside. The power right now is a 1, so to raise that 1, it goes to 2, and we have to divide by the same number that we're raising it to, and then add c. And now to figure out if we're right or not, we can always just take the derivative to check. So the derivative, 3 halves x squared plus c, the derivative of that, we bring down the 2, so it's 3 halves times 2 x, and then c goes away, which is 3x, so it checks out. Here we have 3 examples. Some of them we're going to have to rewrite before we can take the integral of it. For example, this first one, the same thing with derivatives. When we have a power on the bottom, we have to bring it up to the top and make it negative before we can take the derivative or integral. So in this case, we have to bring that 3 up, which would make it x to the negative 3 dx. Then we take the integral of that. We have to raise the power, so you raise it to negative 2 and divide by negative 2, and always have the plus c on the end. And this simplifies to negative 1 over 2x squared plus c. Okay, the second one, it's currently the square root of x. We need to rewrite that as an exponent, x to the 1/2 dx. And then we take the integral, so we raise the power 1 and divide by the same number plus c. We're never going to leave our answer like that where we're dividing by 3/2 because we can't divide by fractions. We need to rewrite that as multiplication. So instead of dividing by 3/2, we multiply by 2/3. And that's our final answer. Okay, the integral of 2 sine x dx. So rewriting this, only thing we'd have to do is bring that 2 out to the front, just realizing that we don't take the derivative of that, or the integral of that, that's just a constant. Then if you need to look on the previous page, we're pretty much just asking ourselves, what do we take the derivative of to get a positive sign? Well, it would be negative cosine plus c, which is negative 2 cosine x plus c. I had a question, somebody asked me, well, do we need to put that 2 with the c, 2c? Well, we don't have to because it's a constant. So 2c is still a constant, so you actually don't need to write it as 2c. It is implied, but you don't need to rewrite it as that. Okay, integrating polynomials, so instead of just one term, we're going to have multiple terms, so you just take the integral of each term just like you would for a derivative. So part A, we're actually taking the integral of 1 dx, that one was kind of hiding. The integral of 1 is x plus c, because if we think about it, we have 1 x to the 0, so we raise the exponent to 1 and divide by 1. That's how we get just regular x. Now we're taking the integral of x plus 2. We take the integral of each individual term. X turns into x squared over 2, and 2 turns into 2x plus c. C, the 3 stays out front. We're really only concerned with the exponents. It gets raised to a 5 and divide by that number. The second gets raised to the third, and we divide by that number. The x is the second, we divide by that number, plus c. Okay, so this example, it looks like we have no idea how to do it because it doesn't really fit any of the problems we've done so far. Well, what we're going to do is divide each term by the square root of x. So x divided by the square root of x plus 1 divided by the square root of x. And that's what we're taking the integral of. So x divided by the square root of x is the square root of x, or x to the 1/2, and 1 over the square root of x is x to the negative 1/2. We take the integral of each individual term. So x to the 1/2, we have to raise the exponent to 3/2 and divide by 3/2, plus x to the 1/2 divided by 1/2 plus c. Instead of dividing by fractions, we need to rewrite this. As such, and we can always take the derivative of our answer to make sure that we get back to the original. Okay, another rewriting before we take the integral. This is the same thing as 1 over cosine times sine over cosine. And knowing our basic trig identities, 1 over cosine is secant, and sine over cosine is tangent. And there is a trig identity where if we took the derivative of it, we would get secant tangent, and that's what we're trying to think of. So the integral of secant tangent is secant plus c. Okay, so every time we've had that plus c, but now we're going to have this particular solution where we have to do an extra step after we find the integral to find out what that c is, so we have a particular c value instead of just c in our answer. So if we need to find the general solution where f prime of x is equal to 1 over x squared greater than 0, find the particular solution that satisfies the initial condition f of 1 equals 0. So the f of 1 equals 0 is what we're going to use to find out what our c is. So we take the integral of x to the negative 2, which is x to the negative 1 over negative 1 plus c, or negative 1 over x plus c. And then what we're going to do is set our function equal to 0, because of this over here, and we're going to plug the 1 in for the x to find out what our c is. And we get 0 equals negative 1 plus c, so c equals 1, and we would rewrite our function, capital F, as negative 1 over x plus 1. Okay, I'm going to do some examples on the bottom here. We would rewrite this one as 2x to the negative 1/2 dx. Take the integral and simplify. Dividing by 1/2 is the same thing as multiplying by 2. So we would have 4x to the 1/2 plus c. On this next example, we need to square it before we take the integral. We can't really deal with the squared right now. So t to the 4th plus 2t squared plus 1 dt. Take the integral of each individual piece. T to the 5th over 5 plus 2t to the 3rd over 3 plus t plus c. And I'm actually okay with you leaving it just like that. The third one, we need to divide x squared into each term before we take the integral. So x cubed divided by x squared is just x. And the next one is 3x to the negative 2nd. Take the integral of each term. X squared over 2 plus 3x to the negative 1 over negative 1 plus c. X squared over 2 minus 3 over x plus c. And our last one, we need to distribute that x to the 1/3 into both terms in our parentheses before we can take the integral. So that's going to be x to the 4/3 minus 4x to the 1/3 dx. When we raise the first exponent, raised to 7/3 divided by 7/3 minus 4x to the 4/3 divided by 4/3 plus c. We can't leave our answer like that. We have to rewrite it as 3/7 x to the 7/3 minus 3x to the 4/3 plus c. Okay, so velocity problems have been very popular for derivatives. We're still going to have velocity problems for integrals, only this time instead of starting with the position function and moving our way down to acceleration, this time we're starting at acceleration and moving our way back to position. So what we know in this problem is that a ball is thrown upward with an initial velocity of 64 feet per second and the initial height is 80 feet. Find the position function, giving the height s as a function of time t. So we were given initial height of 80 and initial velocity, which is the same thing as s prime 64. And obviously our acceleration, since we're dealing with feet per second, our acceleration would be negative 32 feet per second squared. That's our acceleration always. So this time we're going to start with that. And we're trying to find velocity, working our way backwards. That would be the integral of acceleration. So the integral of negative 32 is negative 32t plus c. And then we're going to use our initial condition, s prime of 0 equals 64, to find out what c is. 64 equals negative 32 times 0 plus c. So c is 64. So our velocity function is negative 32t plus 64. And now we can work our way back from that to figure out what the position function is. It's the integral of the velocity. The integral of velocity is negative 16t squared, I already did the dividing there, plus 64t plus c. This time we're going to use the initial condition s of 0 equals 80 to find out what t is, or what c is, sorry. We're going to put the whole function equal to 80 and put 0 in for all the t's. So c equals 80. And our position function, which is the part A, is negative 16t squared plus 64t plus 80. Now for part B, they want to know, when does the ball hit the ground? Well, we would set the position function equal to 0. This is for part B. And there's a couple different ways we can do this. Let's just do it by hand. We can factor it. We're going to take out the negative 16 to make this easier to factor. T squared, that would be minus 4 minus 5. This is t minus 5, t plus 1. So our time is 5 seconds. And that was our section 1 intro to antiderivatives and indefinite integrals.